Spanish. The president is Annie McNeil, who's here in front. Annie asked me to introduce this talk today because I had a close association with Kevin in CSIRO when I joined in 1991. Kevin actually appointed me. And I worked very closely with Kevin for about 5 years then, before his very sad death. We've got Kevin's family here today, which is fantastic. That's really great that the family came along to hear this lecture. Eric Smolders is Professor of Soil Chemistry and Environmental Chemistry at the Catholic University of Leuven in Belgium. Eric actually spent a 1-year sabbatical here in South Australia and worked with Kevin in 1993, I think it was.
Yep.
Spent 12 months here, so he worked very closely with Kevin in that time. And it was very fitting, we thought, rather than bringing an international guest in who didn't know Kevin, we brought somebody in who actually worked with him, and worked with him closely, and worked in the very same area as Kevin in terms of trace elements in soils and using isotopes to look at trace element behavior. So thank you again all for coming. It's my pleasure to introduce the Pioneer in Soil Science lecture for this year, which is based on soil chemistry. And it's an album. Eric.
Okay. Okay. Hello. Good afternoon. Thanks for coming, and thanks for inviting me. It's a great pleasure to do that. I'm not going to talk about my own work. I'm going to talk about the work of Kevin. And it took me a while, to set up this lecture because I had to read these old papers. I'm not sure for the young scientists if they do that, papers of the 60s, to read a paper of the 60s. It takes a while. That's very rich. Kevin published about 60 papers, that I found on Web of Science. But he published a lot more, I think, in internal things. But the papers that he published are really worth reading. I didn't read them all, 60 papers, but I read before already quite some papers, but now I took the time to sit down and read some of the papers, and that was really inspiring. Yeah. So you will hear a lot of Kevin talking today because I took quotes from his papers. It will be, sorry for the family, sometimes a bit technical, so it will go into the chemistry, but okay, just remember the emotions then and forget about the techniques. Right, there we go. So it's about trace elements in soils, the conceptual things, the data, and the pioneer of these, Kevin Tiller. So here we go. Goes slow. Right, what are trace elements? Trace, the name in itself, they are present at very low concentrations. Very low, but they can be essential or can be toxic. The concentrations we talk about are really small. We talk about milligrams per kilogram, a few milligrams, up to 100 milligrams per kilogram. For those who have not worked in a lab, if you have to weigh 1 milligram on a scale, you hardly see the particle, and you dilute that then in 1 kilogram of soil, try to find it back. It's really, you have to be a good analytical person to find that back. And Kevin in the beginning, has spent a lot of time on analytical chemistry. He was surrounded by good people with good skills on analytical chemistry. And if you work on trace elements, you need good analytical people to go to 1 milligram per kilogram, 0.1 milligram per kilogram, or even lower. It is important. Some of these elements are essential at that low level. So if you have a little bit too less, plants do not grow well. If you apply a little bit to the soil, plants tends to grow better, or animals are more healthy. A typical example from Australia is the cobalt deficiency. They added cobalt is not really essential for plants except when there's nitrogen fixation, but the animals suffer from cobalt deficiency if there's not enough cobalt in the soil and in the plant. And if you add a few hundred of grams per hectare, you overcome that. So imagine a few hundred of grams, that's 2 handsful, you throw it in 1 hectare, and animals have not the deficiency symptoms. Yeah? So very low concentration, but can be very active. Here is a range of metals that are essential for plants, essential for animals. And in bold are the elements where Kevin worked on. He also worked a bit on boron and on molybdenum, but not, let's say, as large as with manganese and cobalt and zinc and copper. So he's certainly most known from his work on cobalt and zinc that were really there, in which he made big, large breakthroughs. Now, these concentrations, if you look at these numbers in terms of moles, so they are up to 1 millimole per kilogram, but typical a bit lower, these concentrations are much lower than what a soil can bind maximally. We typically have cation exchange for cationic metals. We have cation exchange capacities of, well, let's say up to 100 millimoles of charge per kilogram of soil, or oxyanions such as arsenate and selenate and molybdate. Oxyanions can bind to 20 moles. That's much more than what is present, which means that the trace elements themselves do not largely affect the chemistry of the soil. It's the soil that dictates how they are bound. And they only occupy very, very little amounts of binding sites in the soil. Yeah? So trace small but very active. There's not only essential elements, but there are also the toxic elements such as cadmium, lead, and arsenic. And it's quite logical that Kevin used his work of the 60s on nutrients to then go in the 70s to environmental issues, the metals that are very similar to these essential elements. So he worked a lot on cadmium and lead and a bit on arsenate because they have similarities with the nutrients he used to work with in the beginning. So he started more as in the framework of productivity, agronomy, and then moved into the environmental sciences. Again, analytical challenges are large. Nowadays we think, okay, I have a sample of soil, I send it to an analytical lab, they will give me an answer and it will be correct. At the time when Kevin started, analytical challenges were really large. I'm looking now to Bernie to see whether he agrees with my qualitative list of detection limits. But in the 60s, they had just a flame AAS, and then you could go as low as 50 ppb or sometimes a bit lower. But that was it. And that means that some environmental problems with low-level metals were not detected. The big disease in Japan on high cadmium in the rice, originally in the 50s, they thought it was just a disease, something endemic. They didn't know it was cadmium. It was only until the 60s when the flame and then the graphite furnace came at the end of the 60s where they could detect the low concentrations at which the toxic effects were already acting. So nowadays we take it for granted, but at that time when Kevin started, these things were not simple to do. So in the 70s, the graphite furnace came, and that the detection limits were lower than, of course, a factor of 10, certainly, or even lower than the graphite furnace. You can knock it down to even 1 or lower than that. And then in the 90s, the first ICP-MS came with detection limits which were even better and certainly more easy to operate. Nowadays, ICP-MS has much lower detection limits, and if you go now to the high-resolution ones, they can go to even, let's say, 0.001 microgram per liter. That is possible as long as you don't have contamination. But see what an evolution that is. It's almost a revolution in detection limits. And in the beginning, of course, it was very difficult. And you can see that when you look at the quotes of his original papers. Well, when he started in 62 on cobalt, the amounts of cobalt in the soil solution are not known, but they would be somewhat higher than the values ranging from 1, and then it's 1 microgram per liter. But it was not sure how much that was. He estimated that it was something like that. And for those who are doing analytical work, this is the whole paragraph to analyze zinc around 1972, a whole description of the procedure to concentrate zinc. If you are below 0.2 ppm, so 200 ppb, you had to do a lot of work, not only typing this text, but a lot of analytical work to detect the zinc. And now you just go to analyst and you give it to your ICP-MS specialist and he will give you a number. But at that time, to discover that, it was a lot of work. And for sure, a lot of work went into that. Why is a soil chemist needed to unravel things of trace elements? Perhaps I didn't point that out in the beginning, but Australia is a continent of trace metal deficiencies. It's an old continent, old soils, highly weathered soils, so the totals are already, the total concentrations are older because after highly weathering or an extensive weathering, the metals disappear to deeper layers. So it's not surprising that many of the trace metal deficiencies were discovered. Manganese deficiency was discovered here in Australia. Cobalt deficiency was certainly well described here in Australia. Now, why do you need a soil chemist? Why not only plant physiology, plants that overcome that things? Well, it's because the total concentrations of that metal in a soil doesn't dictate the problems associated with it. So the total concentrations, the total zinc in his soil, is not predictive for the uptake for the bioavailability. And that's, for example, illustrated in old work that he did 1972, where he related zinc uptake in plants. So here, either concentrations of zinc in clover or uptake, so biomass times concentrations, with all indicators of the bioavailability. And the total gave an R value of 0.4, not significant. So all the way through, nothing significant, neither for clover, nor for wheat. And when you went to concentrations like extracts of the soil, magnesium chloride, calcium nitrate, calcium chloride, he had much better values. So he knew already that time it's related to what we call the intensity, the concentration in the soil solution. Let's say the solubility of the zinc dictates the availability of zinc. So, and that's, of course, it was inspired by the knowledge, agricultural knowledge, that soils that are deficient are the high pH soils with low total concentrations. That is generally known. But he did that chemistry on that and showed, okay, we need the chemistry to unravel the bioavailability. And the concept, which was around there in the already, I think, in the 60s, perhaps the older people here can correct me if I'm wrong, but at that time already, based on modeling and all the data and nutrient solution, the idea was that the bioavailability of a metal in soil is controlled by the concentration of the ion in soil solution. Here there's an ion, for example, the free ion in the soil solution. Here you have the soil particles. Here you have the biological compartment, the root cells. So the metal has to come into solution and bring it into the root cells, which suggests that you have to measure the concentration in a soil solution, the free ion, which at the time of when Kevin started was not possible. Free ion activity measurements in soil solution was not possible until, let's say, the 80s. At that concentration. But of course they took indirect measurements and they used a lot of chemistry to estimate that free ion concentration. So what controls bioavailability? Directly this, but indirectly the soil minerals are involved because they replenish the soil solution. So that it's the amount in the solid, the total available amount, that replenishes within a given time the amount of metal here, and that can move to the roots. Of course, there is biology involved because the roots themselves modify the chemistries around, but that is something that's more the biology, and it's not really Kevin who studied these rhizosphere processes. Okay, a good reason then to go into the soil chemistry of trace metals in general, and then more in particular the work that Kevin did. I think at the time when Kevin started, mineralogists and soil chemists were a bit two different groups of scientists, and I think they continue to be so. Mineralogists, not that soil mineralogists are not soil chemists, but you have people really working in soil mineralogy, they know, of course, but you have these pure mineralogists, geologists, who will say, well, if you know what minerals you have in soil, then you know the chemistry, because the mineral, if you know the solubility product of the mineral, if you can say, well, this mineral is present, for example, a mineral that has zinc or a mineral that has cobalt, then if you know the solubility product, there you are, you know the chemistry. Soil chemists, they work more with reactive pools. Think about it, if you work on carbon or nitrogen or phosphor, you work more with pools. You know that it's often operationally defined labile pools, or pools that replenish the element within a given time. And organic matter people have the different compartments depending on the age and the degradability. Well, the same thing happens also with metals. You talk about reactive pools, whereas the pure chemists often talk about minerals. Now, I found back in the literature a lot of discussion from Kevin against some soil mineralogists. Is it now a mineral that controls the solubility, yes or no? And Kevin was a strong defender of the concept that it's sorption and not solubility of a mineral that controls the solubility. Here comes some technical things, so perhaps if the family is chemist, they can follow this. It's very simple, chemist. Now, the minerals that may control, for example, zinc, is zinc oxides or zinc carbonates. With zinc oxide, it's the most easy to explain. The thing that Kevin always defended in his papers. So if you have zinc oxide, and this is the reaction, it goes to zinc 2 plus and to a OH minus. Then you know if it at equilibrium with the zinc oxide, you have this solubility product which says the activity of zinc and the activity of the OH minus to the square must be constant. Which means that if you raise the pH by 1 unit, so you increase this by a factor of 10, because pH is a minus log of the proton activity. If you increase the pH by 1 unit, so the OH minus by a factor of 10, this goes up by a factor of 100, and this should go down by a factor of 100. So if the pH goes up, zinc in solution goes down by a factor of 100 if the people on the left are right. Yeah? So on a log scale, it looks like this. The log of the zinc activity is A plus 2 times pH, and this is the famous slope where it was all about in the discussions in his papers against, I would say, the Lindsay group for the people, the soil chemists among you, the Lindsay group of America. This is a bit complicated graph, but I'll guide you through. This is a graph of 1972, and where it, I think, first started these discussions. Kevin took different soils and extracted them and measured, in fact, the solid-liquid distribution either of an isotope or of the stable element, but I will go through these details later. But this is the log of the KD, or the sorption strength, versus the pH. Ignore these points to the right. At that time, he had the drawing office made nice compilations of data. We wouldn't do that anymore, but well, forget about this, the left side above this line. Log KD versus pH. And these are the dots, all different soils, and it had an average slope of about 1, well, I would say it's a bit less than 1, but certainly not 2. It should be much steeper, that KD versus pH. And he argued this shows that can't be the case that minerals control the solubility. Otherwise, there would be a much stronger effect of pH on the zinc solubility. So that was one of the arguments. Another argument that, well, that I found back only this morning, oops, this here. Kevin has a paper in Nature, did you know? 1967, we would all like to have that. It was on zinc sorption on clays. Kevin also worked with model systems, pure clays, pure organic matter, you know the discussion, pure iron oxide. Is that valid? But at that time he used pure systems, and he noted that in the presence of silicic acid, the sorption to clays was enhanced. And he considered perhaps its precipitation on the clay, or there is a pure precipitate forming just silicic acid with zinc. And he did studies, and his conclusion were, well, here's the effects: sorption of zinc and concentration of zinc. With increasing concentrations, you have more sorption, and in the presence of silicic acid, you have more sorption than in the absence. And there was no indication on these graphs that it is a precipitate that formed. And he made a whole case with other points and said there is no indication that within the environmentally relevant zinc range, there is precipitation. He pushed up the zinc and he pushed up the pH, and then he had precipitation, but not in the concentration range at which normally you find it, the concentration that you find in soils. Look what I found this morning in a book. One of his last papers, it's in that conference proceedings of '96, he expressed some concerns with EXAFs. At the beginning of the 90s, the EXAFs came up. So at the synchrotron, you can measure more accurately at low concentrations minerals, measure or identify or surrogate for metals or things that the surroundings of atoms that suggest these minerals are present. He was a bit concerned with the EXAFs for the reason that it will add credibility to the idea that there is a control of heavy metal solubility by compounds which may well not apply to the more normal range of soil contamination. He is right. Well, that's my personal experience. We also had discussions. We did also EXAFs, and we had discussions whether these minerals are of any importance for controlling the immediate solubility. And there is still diverging views after all these years. And with that EXAFs, indeed, the whole thing came up again. We have argued, and Fien de Grijs, who is here, that in papers that no, it's not solubility controlled by pure products, but it's sorption that controls. But it's I found it quite striking that he mentioned that explicitly in a general overview of trace metals. Okay, let's now go to sorption. He was convinced, Kevin, that sorption to a surface controls the solubility of zinc. How does that work? Well, already in his earlier days, they knew that sorption was not specific. Well, specific means that it's not like just another cation, for example, zinc or cobalt or nickel, are not extractable by ammonium acetate or calcium chloride, by which you normally extract the ion exchange, the exchangeable cations, the base cations, magnesium and so on, from a soil. Already, I think in 1936, the first paper was shown that, zinc and nickel, they behave differently. You cannot extract them easily with just a neutral salt. So they bind what is called at that time specifically. And the factors, qualitative, that control the sorption, I highlighted them here in red, is first of all pH is the factor that controls the sorption. The time of the reaction, the longer you wait, the stronger it is bound. And the actual mineral species present, the surfaces, reactive surfaces. These three, and Kevin investigated these processes in more detail, but he added something else, and I will go to that now. Let me guide you through these graphs. If you want to understand sorption reactions, the classic textbooks start with this, an adsorption curve. You have the adsorbed species on the y-axis and the x-axis, the concentrations in solution. With increasing in solution concentration, you adsorb more, and in the beginning it's a linear trend. But then, as the whole sorption site fill up, then of course the sorption becomes less efficient and the surface is covered and then nothing is sorbed anymore. Classic things. Now, you want to study metal sorption in soil. You want to know how much of the metal is adsorbed in my soil sample as it is on the field where my crops are deficient. So you take a soil and you want to know how much is adsorbed. You can measure what is in solution, but how do you know what is adsorbed? You can measure the total concentration, but how do you take that pool that you think is quite important for bioavailability, because that's the pool that replenishes it. So you cannot take a soil and take soil solution and you have it. No, then you have only a point on the x-axis, but nothing on the y-axis. So you have to find out how much is adsorbed. And you can do that I think, in three ways. The first one is you just do an adsorption isotherm, but you start here. What you plot here is not the total concentration, but just the adsorbed metal. You start here, you take your soil, you extract it, and you have something here on that point. Yeah? And there's nothing adsorbed at that time. Just that's what you have. Well, nothing. There is adsorbed, but you take that. The adsorbed is 0. Then you increase, you add some more, shake it, let it react. Something goes to the solution, something goes to the solid phase, and something remains. You plot what remains, and you calculate what is sorbed, and you have a start of a curve. You can extrapolate that to 0, and this yellow part is then the amount that is adsorbed in the soil here. That's one thing. So it's an extrapolation, and all the students will know that extrapolation is no good. It's not so safe to extrapolate. It's better to interpolate. But that's one part. Another part is that you do an extraction, that you have already something that you anticipate that's the sorbed pool. While in the extreme, let's assume that you take a total concentration. So you start with your point here, and you plot it, for example, to the total concentration. You add more, you do again a shake and react and do total concentration again. You have this curve, and then again you extrapolate. This part then is then the labile sorbed part. You can do that more precisely if you take an extraction that is more weak, for example, an EDTA or DTPA extraction, and then you start already almost to the point here, and you will have it more precise, your adsorbed pool. But again, it's not so simple to do that on deficient soils of zinc, of manganese or cobalt, because what you have is so close to 0 already at the start. A third method, and that's the method that's really the technique with which Kevin became famous, and techniques that we still use up to now, up to date. Well, not everybody in the world, not all the soil chemists, but at least we do. That's the isotope dilution method. Now, I will explain that a little bit more, because I think we'll come back a few times. So, this is the conceptual scheme. You have a solid phase and a liquid phase, and these circles are the ions in your system. For example, zinc. On the solid phase, you have adsorbed and you have zinc, perhaps present in minerals, all different forms. But at the beginning, you don't know that. And then you add a tracer. And Kevin used a lot of tracers. For zinc, he used zinc 65. And you add the tracer in a known amount. You have to know how much you introduce in the system. And then you let it react, and it will, of course, the isotopes will go to the surface and will exchange with the stable analogues. And the longer you wait, the more of the isotope will penetrate into your solid phase. But after a given time, it's enough. Then you say, well, 1 week or 2 weeks, no, I stop my experiment, I want to write up my paper. No, you stop at a given time when the change is not significant anymore over time. Now, what is that radiolabile pool or the labile pool? Well, you calculate your specific activity, which is the ratio of this to this here, and you say, well, what do I have on my solid phase with the same ratio? And that's my labile pool. To make a simple analogy, imagine that you have 100 units of isotope at the start. You know your units. You shake it, 2 weeks, and then you find only 1% back in the system. And then you analyze how much of the dark dots you have. For example, in the whole solution you have 1 milligram of zinc, for example. Okay, 1 milligram here, 1% of my isotope here, 99% of the isotope sits here, 99 milligrams of my labile pool is here. So your total pool is then 100, 99 plus 1 is your labile pool. And for example, you have a system with 150 milligrams in your system, then 100 is labile, and this one is something I forget about. This is just fixed and does not participate with my chemistry of my solution within reasonable time. Because if Kevin was living for eternity, he would let it go until here, and then everything becomes labile. But that's not so relevant in all things that we do when we talk about plants that grow annually, etc., etc. So that's the labile pool. So when you can measure that with isotopes, you can have adsorption, let me go back here, you can have adsorption isotherms that really start here. Sorry, you start here. You can quantify that labile pool quite accurately, and then you can have your adsorption isotherms that really go to the 0 point. This is then the labile pool, which you can quantify. And he did that, I think, first for cobalt. That's the first paper I found with isotope exchange. Perhaps the family can correct me if I'm wrong, if they would remember what he did in Vienna at the Atomic Agency. Or he did it here, perhaps. Well, the older people may correct me then later. He did adsorption envelopes of cobalt to understand the cobalt chemistry. And something that came out and which is really important, that's what I said, that's the fourth point after pH reaction time and sorption surfaces. He pointed out the sorption non-linearity. This is here the sorption strength as a function of the cobalt that is present in the ion exchange pool relative to the cobalt binding capacity, the maximum. So how much of the sites are occupied compared to the total. So 1, 2, 5, it's not a linear scale, 10, 20, and so on. So the first 5%, the cobalt is bound far more efficiently than in the other high percentage. And that's something that you cannot pick up with a standard analysis of what we call cold cobalt. You need isotopes to measure the affinity at very low concentrations and to identify that at very low concentrations, things become really, really immobilized. And that's important for the whole deficiency side. You can study effects at higher concentration, the chemistry at higher concentration, but it has quite little relevance for the lower concentrations. So if you want to work at the environmental relevant concentration, you have to face the reality that analytical chemistry is terrible or difficult, and you have to accept the challenge and go for it. So isotopes are really the tool to do that. At that time, isotopes were, in fact, the only tool. Do not forget, when you work with isotopes, you count atoms. Tick, 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 each time you hear the tick on the Geiger, it's 1 atom. So you can work at very low concentrations. He did that also for zinc. For the sake of time, I'll skip that. But for zinc, again, well, this is the slide. The explanation of the slide, I will leave it. But this one was the KD value, the sorption strength of the cold. And this one of the, sorry, this is the cold, and this was the hot. This was the isotope. And he found, so he plotted this to the pH. And there you have the left graph to the pH. A bit funny graph, so it's in fact 2 graphs combined. And he found here it goes up to 1,000 in high pH source with pH 8.5. KD values go up to a factor of 1,000. Here they go up to a factor of 100. And he said, oh, higher values of QY, quantity intensity, with the isotope metals are found. And he said that is interpreted as being the result of nonlinear isotherms rather than an artifact. And it's, of course, these sources that are the most relevant for all the deficiency work. I went in detail through one paper on manganese, and I'll take you these, remember, these, for the, sorry, cobalt. These these sorption isotherms that he did in different sources. And he concluded this from the work on isotherms, sorption, and sorption strength. The binding site capacity was best correlated with manganese in soils. That's one thing. So he did different soils. The more binding, the more manganese. The more manganese, the more binding. The isotope exchangeable manganese is proportional to an extract that extracts also manganese oxides. And then also that the affinity, the initial slope in these sorption curves is quite homogeneous among soils. It suggests that there is one similar sorptive phase. And this led to his conclusion that most likely manganese minerals have a dominant role in the sorption of cobalt. I found this quite impressive that he uses all different lines of evidence from his old study to come to the conclusion and not use just one method and go to the conclusion as we often do now. It's a whole weight of evidence. Good work. Okay, then something on the binding mechanisms. How does that bind these metals and where do they bind in soils? Well, you have, of course, logically different sorptive surfaces. You have the organic matter in soils, you have the iron oxides, you've got the clay minerals. The specific sorption is nowadays described as this. You have a surface hydroxyl group, either on oxides, either on organic matter, or at the edges of clay minerals, and then you have these inner sphere complexes that form, releasing a proton, or at least the proton is competing, and therefore pH is the major factor controlling sorption of all these elements. Ravi Naidu showed that you can even have cadmium sorption in soils that have a net positive charge, so in variable charge soils below the ZPC, so you can have it even against the electrical potential, so it really illustrates specific sorption. What about these reactive surfaces in soil? I mean, is it now important to know exactly the mineralogy, the organic matter quantity and quality, the oxide concentration and quality? Well, Kevin worked a lot on model systems, and for the older soil scientists among you, you know that there is a discussion whether it is valid to work on these model systems, on pure clays, on isolated oxides, whether they have any significance to soil. So let's hear what Kevin thinks about it. He worked also a lot on whole soils and on clay fractions, so they extracted the clay and worked on the fractions only. So it was clear that the different surfaces have different binding strengths and different selectivities for metals. Not going into all the details, here is a list of all different clay fractions from different soils, a clay fraction, and he measured the different affinities for different metals, cadmium, zinc, and nickel, and compared it at the same time, and he found out the order of selectivity changes. If they are dominated by iron oxides, then it's usually zinc binding stronger than nickel, binding stronger than cadmium, whereas on organic matter they all bind a bit similar, and then in clays it depended on the pH, and all these things led him to conclude, okay, it is complicated and each of the surfaces has its own characteristics. Now, at the moment, as we speak, 2011, what is around now for predicting sorption of metals? We do it with modeling. We teach our students the models and so on. Of course, in these models, we know that the different surfaces have different binding strengths and different selectivities. But there are two schools, let's say, around. I mean, there's something in between as well, of course, but two groups can be separated. The people who like the empirical partitioning models, so just, well, just to put it simple, you have some soil properties, you put it in an empirical equation, and you have your sorption strength. It sounds very empirical, but of course there is some conceptual thoughts in there. And then you've got these addicts of the multi-surface models that say, okay, I will analyze clay with this, iron oxide with that, and then organic matter with this. And we have these all these models developed by the organic matter people, by the oxide people, by the clay mineral people, and we bring all these models together in a nice software, and then we have a mechanistic model based on first principles without parameter adjusting. We get and we model the whole soils. Fien de Grijze did a bit of a comparison of these models, and she was a bit critical about it, because she said, well, these multi-surface models, the prediction of metal partitioning is perhaps still unreliable. Well, it seems still unreliable at present. I'm quite confident that the addicts for multi-surface models would say, nah, we disagree. No, these empirical models, But let's hear what Kevin said already in '62 and then again in 1984 about all these things. He can speak because he did both. He compared both. Caution must be exercised in the extrapolation of data gaining using minerals. And in 1984, with model systems unlikely to provide the means for quantitative prediction. So he didn't like it. I knew it. So analytical aspects of metals in which Kevin contributed. One of the things, the Clayton and Tiller paper of 1979, the method that is still used by many people around, is the EDTA extraction. I won't give you much detail, but there's a long paper with all the technical issues and the discussion of the chemistry behind it, and okay, that was then the proposal, given shaking time, and so on. And then something with, I would say, I can't say that I would agree with everything that Kevin did, also something with which we disagreed, or we found it a bit strange. When Kevin worked at IAEA, and there was a whole discussion among the isotope freaks about isotope fixation. Let me explain it. In calcareous soils, Kevin found something really strange. He changed that method for the E values for the radiolabile pool. And in acid soils, so soils with pH below 7, these are all different procedures. Don't bother about the procedures, but you should have always the same value, whatever procedure you take. It's about reversibility of reaction. It worked, no problem. Okay, there is a bit, goes up and down a bit, but no problem. Calcareous soils, one method, 4 ppm, another method, 46, 23, 12, 45. Of course, he had some problems with that, and he admitted in a paper that does not work. And they attribute that to isotope fixation. The soil is so hungry of dying for trace metals, you add an isotope and the isotope will go to the soil, fix it, and it will not exchange anymore. Now, I must say, it's not that he completely believed that idea, but at that time there was a big debate about phosphor fixation, and it had relevance for phosphoric fixation in soil and so on. I looked at the text with a discussion today again, and I found it a bit difficult to say, and I had the impression that he also struggled a bit with that isotope fixation idea. But it took us a while to find out, and we were really interested in this. And in fact, what we found out later. There's a lot of discussion with Mike and Enzo and many people, then also with a Swiss group about it. So what you in fact assume in that isotope dilution, that everything is the same, that there is zinc 2+ in solution. But in the solution there could be also other stuff that you measure on your AES or your graphite furnace as zinc. But in fact it's not zinc, it's zinc that is occluded and not isotopically exchangeable. Colloidal stuff that screws up your method because you think that everything here in solution is labile by definition. But this may be not labile and not plant available. And it's persons like Enzo here present cleaned up the situation with a cleanup procedure. So shaking the soil and putting in a resin, and on a resin only the reactive metals bind. So the zinc 65 as an ion, but also the stable zinc. And he found that indeed at high pH there is a difference with the E-value standard versus resin, and that you overestimate your labile pool when you have not a cleanup. So he also initiated a lot of discussion. So we did not agree always with what Kevin found, so it initiated some discussion. And it was an interesting time between 1996 and 2003 when we all set up these things. Okay, I have to speak a bit quicker for the reaction kinetics because it's already 4:45. Kinetics. Why would somebody be interested in kinetics? Is that something just for the lab, how long you have to wait for an extraction? No, it has environmental relevance. Imagine you're a farmer and you have a deficient soil, you add a fertilizer, your crop grows, and there's sufficient added, sufficient the year after, no fertilizer needed. No, if you take into kinetics, it's possible that the year after your fertilizer value or your residual value is gone because of the slow reactions. They go slowly into the minerals and are fixed. So there was a lot of attention on that in the 60s and the 70s on these slow reactions by which metals are immobilized. One of his, the most cited paper of Kevin is the work that he did in Germany with Brümmer and in Bonn. Is this one? This is on pure things. Is on goethite, where he measured the slow reactions. So goethite are the iron minerals, let's say which gives the red color in the soil. So he synthesized goethite and measured the slow reactions up to 42 days. And what happens is here the percent sorbed as a function of time in the square root of time. Why? Well, I'll explain that. You have an immediate reaction at the surface, outer surface of these particles. They're small, there's not centimeter particles. We talk about nanoparticles. They called it colloids at that time. Should we call it nanoparticles? Well, I'll leave it for the new scientists would always say nanoparticles. Anyway, they did that, immediate absorption, and then followed by a linear absorption as a square root of time, which is indicative of diffusion reactions. And they changed the temperature also to measure the effect of temperature on diffusion. And then it's over. Then Kevin could go home because it's flat, no more need to do further studies. And they attributed to external absorption, diffusion, and then locked up everything what is inside. Conclusion, the results show that goethite, and of course other iron minerals, may be an efficient sink for trace metals, for long-term sink. Now, all that work was used in many follow-up work environmental. It seems perhaps on model systems, just another kinetic study, but it had, I would say, far-reaching consequences for all the work that we did, well, or a lot of work that we did later. Well, first, I'm not sure if there's soil physicists here in the group, but if as a soil physicist you want to learn something about kinetics, chemical kinetics versus physical kinetics, read that nice paper of Rai, who's present here, that he wrote up with Ravi and Kevin about slow reactions that indeed they can affect even transport processes of cadmium, in this case, in soil. But also, this one happens, of course, in terms of the environmental relevance. So what you have on the absorption curve, you have a fresh addition, fresh curve. If you age it, then the curve moves to the left, and you get some metal that is fixed or non-labile. Yeah? So if you plot that fresh aged, initially everything is labile, sorbed by definition, is reversible sorbed. But then as time goes on, it goes from the surface to the inside of the minerals, and then it gets fixed partly. Now, why is that important? For example, for that question, was in fact initiated with the whole discussion about cadmium in phosphor fertilizers. For the younger ones among you, the whole thing on cadmium in fertilizers was not something that Kevin invented. There was early work also from Australia by other people that showed that long-term use of phosphor fertilizers increases the cadmium in the soil because phosphor fertilizers have some cadmium as a residual contaminant. So the longer you wait, the more you will poison your soil and probably bring cadmium into the food chain. In the 90s, this became really an issue. Cadmium was a priority pollutant in the food chain. We had to monitor cadmium in our potatoes. We should not have too much cadmium in the lettuce, and so on and so on. And one of the things that I remember the discussion with Kevin was about the aging. We did some consultancy work here. Well, that 1 year when I worked here, I helped Mike also with on a consultancy job with fertilizer issues. And of course, you predict a long-term buildup, a linear buildup the more you use phosphor fertilizers. But the question was then, if there is some fixation as time goes, the slow reactions into the iron oxide or what have you, they may offset the risk because the labile pool does not increase. It's the total that increases, but perhaps not the labile. So if fixation is an issue, yes or no. And that brought us to develop the labile pool also for cadmium. That's something strange. I must admit, I developed that technique, the radio labile technique for cadmium. There was one unpublished paper by another group on cadmium. And Kevin also did that, and I never found it. And I asked Richard Murray, do you find it? No, he didn't find it. And today I found out that it's never published. It was cited sometimes as unpublished results. So he did that also with cadmium. Now, what certainly is clear, whoever did the first E-value, doesn't matter. E-values of cadmium are generally quite high. Most of the cadmium is labile, so there is not so much fixation, unfortunately. It's a big ion, and it doesn't penetrate the iron oxides. And if you look to the data of the goethite, there is not that much slow reactions of cadmium. It's more for nickel, but less for cadmium. And Mike and Rebecca Hammond, they had a really nice setup that they developed, a really nice test for that aging. They took samples from long-term phosphor trials that were either interrupted, called the rundown, so until 1975 they added phosphor, and they had another pair of soils where the phosphor was continuously added until the day of sampling. Well, until the day of sampling, they had, of course, the continuous phosphor application had more cadmium because they had received more phosphor, and these rundown plots had less cadmium. Now, the point was, is the labile pool higher in the continuous phosphor application, yes or no? Because the continuous phosphor application have received more fresh cadmium. So it was like a time signal, and they found out, yes, there is fixation, but no, it's not large. So in terms of environmental relevance, in fact, for all risk assessment, they have to agree there is fixation, but in fact, it's not large enough to really take into account for the food chain protection. So it remains an issue, the cadmium in the fertilizer. Later than that was the 90s, came all the work in Europe on trace metals. In Europe, they want to regulate everything, and zinc was a priority pollutant, believe it or not. Here it's a deficient thing, but in Europe it's a priority pollutant. And copper is an issue, and they wanted to know what's the limit, how much copper can we add to a soil. And all the ecotoxicologists, these are the people that like playing around with lots of species, they spike soils and test it right away. And of course, the chemist would say, but wait a moment, when you add metal salts, that's not the environmental relevant source, and you have to wait until it's finished with aging. And of course, that started a lot of work on E-value measurements of copper, and in the group here in Adelaide, they measured lots and lots of E-values of copper, of zinc, of cobalt, of nickel, molybdenum, it was like a process going through the whole table of Mendeleev. And this is an example. E-values, for example, in an acid soil, there is even a bit of aging, young, freshly added, and then 1 year aged, and so on and so on. Data were generated, models were generated on aging, and that had, of course, some relevance. For example, for that work that we did with ecotox, if you spike a soil and you have here the soil concentrations of nickel, and here you have your response, for example, a plant growth, increasing nickel decreases the plant growth, logically. But if you wait a year, then it's less toxic because the nickel is fixed, is going so inside the minerals. And perhaps this visual picture will help you if you have a field gradient with copper, for example, copper in fungicides or under a vineyard that has received long-term applications of copper. This is not the case, but here was another gradient with copper, aged copper versus fresh copper at the same concentrations. Look at the difference in toxicity and what aging, well, it's not only aging, but what aging can bring. Now, that work that Kevin initiated in the 60s with cobalt isotope exchange and developed further with zinc and cadmium, and that went into the 2000s with all these other metals, is used. So it is used, and I think this is the only speciation method or speciation data that are used into regulations. There's a lot of people that work on speciation with exhaust extraction and so on, and very, very few of that is used. People always say we use that for bioavailability, but the aging data have been used in the EU for the risk assessment of these metals. So how it works is that the toxicity data generated on fresh soils, they are corrected with a factor. The factor is based on toxicity, but underpinned with a chemistry. That was the strength. You can do toxicity on a few soils, but you cannot do toxicity on hundreds of soils. You can do chemistry on hundreds of soils and aging data on hundreds of soils. And that work, the models that have been developed on aging were used to support and say, well, the aging at least explains that chemical aging explains to what extent metals can be fixed on the long term. And these are the factors that have been used in these risk assessment. For example, the factor 3 of zinc, very simply said, if you do a toxicity value with freshly added, multiply that value by 3, and that gives you your long-term value. These values were badly needed for the risk assessment. Without these factors, we would have risk assessments below background, i.e. it would mean no more zinc can be produced in the world because it's toxic. Imagine. So, of course, that I'm stretching it a bit, but these values have been used, the chemistry data underpinning the toxicity data have been used into the risk assessment. Then, the last 10 minutes, please. Environmental issues with trace metals. So it has been most on chemistry so far, just except for the last things. Kevin has moved from pure chemistry and productivity into environmental issues in the 70s. I mean, this was, of course, at the time environmental issues came up all over the world, in the US in the 60s, and then here, I'm sure, in the 70s. And I think Lester told me that the first study on Port Pirie was in 1971. Port Pirie, that big smelter here in South Australia, where there was some health issues, and where in the beginning it was just a matter of monitoring the extent of contamination around Port Pirie. Of course, that was not, let's say, process research, but monitoring the extent of contamination. Just to give you first a little bit, for those who are not aware about that toxicity, cadmium and arsenic, the issues there is the thing that we get on our plate, the food chain contamination. With lead, it's the dust ingestion. Children that are playing around in a lead-contaminated environment and eat soil or dust or lixims, that's the major route of exposure. And then copper and zinc, the issue there, when you have too much copper and too much zinc, is a toxicity to the biota. Plants die more quickly from copper and zinc than people. So we have to do the ecotox. And here's a list, while I looked in the papers and a bit of the work, and it's certainly not finished, on the things that Kevin worked on environmental issues. Port Pirie, emissions of metals from gasoline, emissions of metals through fertilizers, cadmium in the food chain, that was at the time when I was here, and metals in sewage sludge, and Bolivar sewage sludge and other sludges. A bit of that, a little bit of illustrations. He hired an Irish guy to work on spuds on potatoes, of course, and there was an issue here with cadmium in potatoes, and it was unrelated to the total cadmium in the soil. It was related to the bioavailability. So people thought, wow, high cadmium on the market here in the potatoes. It must be from the phosphor fertilizers, because here the phosphor fertilizers that have been used in Australia were quite high in cadmium. It was not the relationship with EDTA extractable, the so-called bioavailable pool. The EDTA didn't explain it. It was the soil salinity, and it's related to something, a complexation of cadmium with chloride, and it brings the cadmium towards the roots and brings it in. The whole field work that started there has initiated, that's the moment I stepped in to do a bit of process work, and which helped me a bit to help my work on bioavailability and fluxes and all these nice things, kinetic things that we dived into. Also, nice, not only identification of problems, but also identification of solutions, the work that he did with Danny Oliver. The cadmium-zinc interaction, that's a physiological thing. So zinc-deficient crops or borderline zinc-deficient crops confuse between cadmium and zinc because they are chemically very, very similar. So the plants dying for zinc take in more cadmium, and inadvertently, of course. And if you supplement these plants with a bit of zinc, then you can reduce the cadmium in the grain and get below standards. Well, these were not above standards, but still it is important. The cadmium thing went a bit down. I think in Australia it's also cooling down a bit on cadmium, but in Europe it's heating up again. In Europe it's really funny. First they increased limits from this to doubling the limits, and now there's a recent proposal to again go to lower limits, and again that will stir up the discussion. I'm sure Canada will again be really upset about these new limits, and they will have to do something about it. Summarizing, what's the pioneering work of Kevin? I think that isotope work was important for the detection limits, for the analytical part, to show the concentration dependency, to quantify pools, reactive pools, and to quantify these slow reactions. They are really important. I didn't talk too much about the absorption mechanism because it would be too technical about the hydroxylated species, hydrolysis products, but he contributed to the mechanisms there at the time at which EXAFs and the synchrotron was absolutely not existing to do that fine work that we can do now. I'm not saying that EXAFs is wrong, don't take me wrong, and my quote there from Kevin was about the minerals that they identified. With EXAFs you can do wonderful things on absorption mechanism. So he did, of course, a big step from agronomy into environmental sciences, and I give here the examples here. And that started, of course, a big group here of environmental issues in Adelaide. It's a huge group compared to the rest of the world that works on inorganic but also organics contaminants in the system. Here he is, the Kevin. We all liked him so much for his no-nonsense attitude. It was pleasant to read. I mean, how he worked with processes. He went into the details of process, but in the end he said, take care with that process research, you have to match it with field work. He didn't like pot trials, apparently. He said, pot trials, is that right, Bernie? He didn't like pot trials, you have to work in the field. He had some clear examples where the trends were even opposites in the pot trials. He worked on the model systems for sorption, but he said in the end, take care, use whole soils or clay fractions. Yeah? And it was interesting to meet him, of course. And the last meeting was, Maggie remembers, it was in Paris in the end of the conference, the COPTE conference, where I danced with a lady all dressed up in red, and we had so much fun that evening. So, and it was, of course, a very nice person. I think everybody who knew him will admit that. Look, I read the papers, pleasant. The first paper, 1958, Analysis of Standard Rocks G1 and W1. I would say, Kevin, what a boring title. But his last paper, Lead in Wine, a study on 2 varieties at 2 wineries Australian. Look, 2003, 7 years after he died. I don't know where he is, but he seems to have a good time there. Thank you.
We normally open up for a few questions, so if people have a few questions on clarifications on soil chemistry, I think this should be compulsory for all undergraduates in soil chemistry to go through this presentation, because it's a lovely historical perspective of how our thinking changed over the years through Kevin's work. Any questions or comments people want to make? No? There's an opportunity to ask Eric questions afterwards. We're going to have drinks down in the Charles Hooker Centre after the presentation now. I'd just like to ask Annie McNeil to come up and present Eric with his plaque for delivering the pioneer lecture in honour of Kevin Tiller.
Thank you very much.
So if you'd like to go down to the Charles Hooker Centre, there'll be drinks and snacks down there. Please join us right here and turn left. Thank you.